Hi, good morning. First of all, I would like to thank the organizer for the invitation and the attention you put into our work to be present in this meeting, that it's very important to us because it allows the exchange of ideas to generate options for health and prevention. In the National Laboratory for Biomimetic Solutions for Therapy and Diagnosis of the Faculty of Science of the UNAM in Mexico, we have several lines of work that have to do with the development of solutions precisely to allow us to improve the quality of life through improved health. In this national laboratory, we participate by biologists, chemists, physicists, mathematicians, engineers, and we combine our ideas to be able to make innovative developments. One of these line of work is the generation of biosensors. As you know, our ultimate goal is to generate what we know as devices to be used at the point of care. We know that these devices have to have a series of characteristics, and we are all committed to achieve this. They must be, well, as you see here, cheap, sensitive, specific, easy to use, that we do not require some big equipment or expensive equipment, or and that they are finally used where is the patient or the person who needs it. Sorry. Thus, the development of these devices or sensors, as you well know, will obviously allow us to react faster to many infections or to contaminating elements in food, water, and prevent diseases. Many of the diseases that we now face, all of them have factors that we can measure and that can also help us treat more effectively and earlier. So in the lab, we have developed a line of biosensors using magnetic beads as the reaction base. Until now, we have used fluorescent molecules as reporters due to the advantage of multiple detection, but this can't be transformed in the same way in an enzymatic reaction. So until now, we have developed sensors for the detection of antigens, as I show you here. And that is to say, any molecule that can be recognized by an antibody. And as you can see in this image, we can work on closed microfluidics chips in which the sample is placed. Sorry, I have to change my pointer. Except where the sample is placed in one of the inlet. In another, there is a reaction with the antibody. It's a competition reaction. And finally, there is an optical detection, as it's shown here in these panels. We have already carried out many tests for detection. For example, hormones as main developed interest, since metabolic endocrine disease are totally on the rise in prevalence and incidence worldwide. Diseases such as hypothyroidism, growth, or infertility. Here I showed you just a graph of hormone detection for prolactin and the correlation of our detection with a standard curve for different kind of samples. As part of a combination of two methods, this is an optical antigen detector and an electrochemical detector for glucose, we have generated this dual sensor, which we can detect with which we can detect insulin, as you can see in this curve, but also glucose by voltage changes. Here I show you again samples, different samples, human samples, even one with saliva, which is very, very accurate with respect to the blood. So the third, let's say, line of biosensor is the detection of the antibodies of which we already have reliable evidence of its operation for detection of antibodies and diagnosis of hypersensitivity pneumonitis, in which we can do using magnetic beads, as I said, functionalize with the antigen, and then we recover the whole primary antibodies in the sample, and we react them with a secondary antibody, which is marked with fluorescence. But I'm going to talk later about this strategy because it's the same strategy that we use for COVID antibodies. But just to initiate, we can do this reaction, all of them, in different ways, even in tubes, plates, or our microfluidic chip. And we already have a lecture device with which we can control the beads and do the detection. So today I will talk more about this biosensor, and I wanted to show you the results that we have from the sensor that we developed for detection of nucleic acids, particularly for the detection of RNA of COVID samples, let's say, of detection of COVID. That is the case in this sensor that the pandemic has allowed us to see is of vital importance. Unfortunately, as you know, SARS-CoV-2 infections and have 100,000 of confirmed cases and unfortunately deaths. And it has reached surprising levels and unfortunately, as I said, a number of deaths. However, viral infections are not new, and we have already gone through other pandemics. We have already gone through seasonal infections, such as the case of the influenza, and something that we must learn from this difficulty period worldwide is that we have to generate options that allow epidemiological diagnosis much faster, much efficient, and that allow us to act in a responsible and timely manner. So as you know, there are different methods for diagnosis detection. Some are direct methods that have high specificity, but they are really difficult to transform into massive and rapid diagnosis tests. Others, such as the serological, are indirect methods that, although they allow the evaluation of a large number of samples and lower the cost, their specificity is much, much lower, and we are indirectly measuring the infection, let's say. So we have seen at all this time on the market, actually for the detection of COVID-19, since we have two types of tests. The PCR test with enormous sensitivity and specificity, but since it is basically a technique for research and monitoring viral strains, the results, it takes a lot, it's quite expensive, and not affordable for most of the countries. Although it was used in this pandemic as massive method. At the same time, we have a great variety of antigen tests were developed for this first time, which although they meet the requirements of being fast and cheap, they do not meet the requirement of being high sensitivity. In the antigen test, it was seen that they have up to 64% of false negatives due to their lower sensibility. And in those of antibodies, despite being cheap and close to the use of the people, their sensitivity is quite low. So thinking on this, what we did was, as I told you, to use the magnetic beads as a base of reaction surface. And as you can see in this diagram, the sample is placed in the first inlet, in this case, we can use the sample purified as by columns or other means, or samples taken in a treatment liquid that allows the virus to be inactivated and therefore make it non-contaminating. So the biosafety label of the development device is quite good. So once the sample is in the inlet, we have a first hybridization reaction that allows the oligonucleotide sound to attach to the genome, the viral genome, if it is present. But then with the beads in a second hybridization process, we will recover the excess of these oligonucleotides that are not hybridized to the genome, to the viral genome. So we can detect both, the ones that are that are recovered by the beads and the ones that stay in the inlet with the genome. So the detection method also has the enormous quality that, as I said, it can be done in multiple well plates, as Annelisa will be, or it can be done in microtubes, or in our microfluidic chip as well. In this case, we illustrate the development of the methods in a well plate, where here you can see the first hybridization reaction, the sample with the oligonucleotide zones. And then in the plate, we do the second reaction, the second hybridization of the magnetic beads with the probe that did not stick to the sample. What this means is, as you can see below in these panels, is that if there is a lot of fluorescence, it means that there was no virus in the sample, and therefore a large number of probes are left over and adhere to the magnetic bead. Not like this, if there is a large amount of virus, there are no surplus of oligonucleotides, and therefore the low fluorescence decrease until reach, let's say, 0. So we can have an inverse relation between fluorescence and viral load. So during the process, we obviously did the necessary validation for all the biosensors and for all the diagnosis methods. We begin by the standardization of the parameters of the elements used in the diagnosis test that allow us to have the greatest dynamic range of detection. And this begins by determining the number of bits, as you can see here, and the proportion of probes that we put either in the bead or in the medium, or in the fluorescence with the medium. So the concentration curves with synthesized probes that represent a differential concentration of the viral gene in the sample. You can see it here, give us, even if all of that give us a good range, there are one combination that give us the greater difference between one point and another. Obviously, we did all the controls as detection method. You see on the left panel what is the typical control. Let's say it's a curve where the amount of synthetic RNA that represents the viral sample increases. Then we see the negative case here, which will be our limit. That means from there to from 1 to plus than 1 would be the negative samples, and below would be the positive samples. Not so for human RNA control, that it would be always positive. So here you can see the controls. It means how much one RNA just bind in a specific to the other, either in the magnetic beads or in the fluorescent probes. And I will not take too much time on this, but of course, everything works as we expected. No, there is no in a specific union between them. And then you can see that we have also carried out the specific controls in which we use other subtypes of coronavirus to see if the sensor has the specificity required. And of course, as you can see here, all these viruses give us a negative fluorescence. And you also can see here our limit of detection if the sample is as this, that is quite clean because it's a synthetic virus. And we can see even 1,000 copies, viral copies. So as in the PCR, this is a hybridization process. So the sample could actually affect the process because in the sample we also have the RNA, the human RNA in great concentration. So as you can see, well, here is always the reference curve, but here what we test is if we control the number of viral copies and we change the quantity of total RNA, we can actually see that there is a change above 70, if the sample has 70 nanograms total, then we can know, then we can actually have false negatives. All the samples will give us a negative result, whereas it should be positive. But this is how the total RNA affects the probe. And we did the same, changing the viral quantity, and we maintain the total amount of the RNA into the probe. And as we expect, we have a curve that detects the different concentration of the viral curve if we maintain the total amount of RNA. So, so far, we have made more than 4,000 samples, and these samples have been classified as expected into positives, of course, and negatives. This is for gene N and for gene E. And we can see that actually our specificity is quite good. For the gene N, we have really few false negatives here. And we have more false positives because as we are using fluorescence, the tendency to have less fluorescence is bigger. But it's not the case for the gene E. These tests give a higher degree of false negatives according to the results and the comparison to PCR. So this allows us to say that in the case of using unpurified samples, let's say we take the sample and we put it in the reaction chain, we have more or less, we have 92% of sensitivity, whereas 80% of specificity. But when we purify the sample, this arrives just to 91%. So finally, I want just to tell you quickly that we also developed the sensor for antibodies. As you know, the body develops antibodies when the virus infected, and this occurs several days later. But it's a great tool for epidemiological studies and to cut the chain of infections. In this case, what we wanted to measure is the amount of antibodies for the whole protein S, but also for the RBD domain, which will give us the idea of how much neutralizing antibodies or total antibodies to the virus the organism develops. So as I showed you before, this is the diagram of the microfluidic sensing chip. And we can see, I already talked to you about this, but here, just quickly, we can see we did the standardization curves of the functionalization of the magnetic bits, the amount of fluorescent antibody, and the detection curves comparing with the normal ELISA. As you can see, our curve is quite more exponential. So we analyzed more than thousands of serums, and we can see that for the ELISA, we have absolute value, even if not all the samples have the same value, let's say 100 or 300 or 900, because it's the value of the titulation, let's say. But for us, as we are using the whole range of fluorescence, we do not see absolute values, but we see a continuum in this range, let's say from 2,700 to 8,100. We actually see a bigger range. So the ROC curves give us, in the case of total detection for protein S, here, an index of 1. In the case of the RBD domain, the index is 0.8. Both of them quite good, actually. And the other advantage of this method over others is that we can do multiplex, not just, of course, for antibodies, but as I show you, for RNA, that we can see gene N and E, and now we are working on COVID and influenza. And then here you can see the detection of EGH, EGG, EGM, for the RBD domain and for the S domain. So we can actually know the level of both types of antibodies in the same sample, but we can also do, of course, RBD and protein S at the same time. And of course, later on, a combination for other infections or multiplex different things. So finally, I show you how we developed this microfluidic chip, but also the device that we made to move the magnetic bits and detect the signal and processing it. As you can see here, you have the inlets of the chip, you have the microfluidic connection, and here you have the bits, this brown spot in each inlet. And then the equipment, actually what it does is to move the bits from one inlet to the other one, and then at the end we have a detector. Let's see, but I have to change. Okay, yes. Now you can see the device working, and here you can see the bits. They will travel into the microfluidic chamber and moves from one well to the other, and even take it, them during reaction. So in this case, let's just finish. They will arrive here. Of course, all the physics involved are already characterized. So in this case, I would like to say that the microfluidic chip, as is a closed device, it does not require to have fluids input or connectors or that you cannot just look at in a microscope. And actually, we are working in the process of lyophilization and everything, so you can carry out. And here you can see actually the reaction is quite more effective, and the results obtained are very good. The same reaction from our on-chip sensors goes with our ROC of 0.9, as shown in this graph, which is quite good. Well, finally, I want to thank the entire team that worked on this 2-year process of COVID sensors, but actually most of them works in this since 2016 for the develop of all the sensors on biosensors. And of course, I want you very much to thank you for listening to me. And well, I leave the page of the biosensors and the national laboratory if you are interested. Thanks a lot.